All right, Advanced Math 8, here we go. We've got lesson 5.3.1, comparing growth. All right, so we are going to look at just the different growth rates as we go through here. So we've got three sequences, A, B, and C, and they all have a different growth rate to them. So let's see if we can try to find what their growth rates are. Oops, my calculator has to. All right, so let's say you come up to one and you're not sure, you can't really tell what it is. Is this multiplication by something or is this addition? I don't know. By eyeballing it, I can't really tell. Okay, so the first thing you would probably do is ask yourself, does it look like it could be addition or subtraction? In this case, yeah, the numbers aren't going completely crazy, not like growing like super fast, so maybe it might be addition. So to double check, we would just do, okay, if this is addition, I can take 54 minus 27 to see how much it added by. So if I do 54 minus 27, I get 27. Okay, now I'm going to check 81 minus 54. 81 minus 54, 27. Oh, that's good. And then 108 minus 81, 27. Okay, it's adding by 27 each time. So looks like I've got arithmetic sequence on this one because we are adding by 27 each time. Sweet. All right, so we know that. Next one. Let's look at the next one, sequence B. So on this one, okay, starting at 9, then we're jumping around quite a bit. It doesn't look like we're adding the same number each time. Let's see if we're dividing by the same number each time, or multiplying. So I'm going to take 36 divided by 9. I get 4. Okay, so now I'm going to check 81 divided by 36. Oops. Divided by 36. 2.25. Ah, it's not geometric. So it's something else. It's not arithmetic. It's not geometric. I can tell it's not arithmetic because if I do 36 minus 9, I get 27. But if I do 81 minus 36, I get 45. So it's not arithmetic because I can see here that I didn't get the same number, the same multiple. And then over here, when I'm subtracting, I don't get the same difference. So it must be something else. Let's do this. From here to here, we said that that was an increase of 27. From here to here, this is an increase of 45. And from 81 to 144, looks like it's an increase of 63. One of the things we can do is check the differences of the differences. So here, difference of the difference, I would do 45 minus 27, and that's 18. And then 63 minus 45, that's 18. So the difference of the difference is constant. What does that mean? It means I started by adding 27, and then instead of adding 27 the next time, I added 18 more than 27, 45. Then for the next one, I added 18 more than 45, 63. So the next time, I'm going to add 18 more than 63, which should be what, 81? Yeah, about 81. And then the next time, I would add 18 more than 81, which is some other number. All right, so difference of a difference. These are actually quadratic. Anyways, next one. 6, 12, that's easy. We're multiplying by 2 each time. So that one's geometric. So we had an arithmetic. We had an other, which is quadratic. and we had a geometric. So there's my three sequences. Now I'm going to graph them. We should know what these two graphs would look like because arithmetic, we know that they make linear graphs. Geometric makes curves, exponential graphs. So we're going to graph each of them in a different color. All right, so sequence A, I'm going to make in my favorite orange color here. Okay, so sequence A is going to be in orange. So 127 is my first one. So I'm going to go to this graph. You'll find this graph in the resource page. So 127, let's see, this is 25, 26, 27, I'm going to call this. So there's 127. The next one is 254. So 254, this is 55, so 54 is right below it. Next one would be 381. 381. My stomach's growling. Next one would be 4108. So 4, this is 105, so 108 would be about right there-ish. All right, we can see there, yeah, looks pretty linear. Sweet. Next one. Let's do the next one in light blue. So sequence B is going to be in light blue here. So it's 1, 9. So it starts way down here. So we're just going to look and see how these grow compared to each other. The next one would be at 236. So 2 and let's see, this would be 35, so 36 would be about right here. The next one would be at 381. Ooh, they're tied. And then the next one would be at 144. So 145 is right here, so this would be 144. All right, that's definitely a curve. You see that? There's a curve going there. Okay, so the first one was linear. Next one gives us a kind of a curve. Even though it starts lower, since it's a curve, it's passing that line. It's growing faster than that line. Okay, the line grows by the same amount each time. The curves start growing by more and more as you go. All right, our last one we'll do in purple. So the first one's at 1, 6. So this one's starting the lowest. So there's 1, 6. Next one would be at 212. So 2 and 12 would be about right here-ish. Next one is at 324. So this is 25, so 24 is right below it. And then 48 is the next one. So 48, there's 50, so 48 we're going to call right about here. All right, so we got 3 different growth patterns here. Our original orange ones right there. And we see that the light blue one, which was our other or quadratic, was curved, and even though it started below, it eventually passed the linear. And then our purple one, the one that came last, we see it started lower than all the other ones. The blue got bigger, but the purple's just kind of plodding along down here, but it's curved. So it hasn't quite gotten to all the other ones yet. All right, so we've graphed them. Describe how the sequences are growing. So sequence A is growing by adding. So A, it's adding 27 each time. Sequence B, and this is constant. Sequence B, it's adding 18 more each time. So it adds 27, then 18 more each time. And that is not constant, because it's adding by a different number each time. Okay, the last one was our purple one. And we saw that it was multiplying by 2. And that was constant. It was multiplying by the same amount each time. It's a different type of constant because it's multiplying instead of adding, but it's still constant. It's the same each time. So arithmetic and geometric, we see that they are constant in their growth pattern. They're always going to do something the same. In arithmetic, it's adding something. In geometric, it's multiplying each time. State the next two terms of the sequence. Okay, so the next term for A, the next two terms, if we're adding 27 each time, we do 108 plus 27 and get, 108 plus 27, we get 135. And then the next one, we'd add 27, and we get 162. Those are the next two terms. For our sequence B, okay, remember we're adding 18 more each time. So I'm going to take 144 and add 63 more, and then 18 more on top of that. So 18 plus 63 would be 81. Oops. So the next one would be 225. Let me make sure I did that right. 144 plus. Yes. All right, the next one after that. So I added by 81 to get to the next one, to get to 225. So I'd start at 225. I'd add 81, and then I'd add 18 more, because the difference of the difference is growing. And that'd make 324 for the next one. For the last one, we're just going to multiply by 2. So 48 times 2 is 96. And then 96 times 2 is 192. All right, there's the next two terms of those sequences. See what happened? C has finally overtaken A. Pretty good. All right, so what if n was the number of years and t of n, the nth term, was the amount of money in your savings account? Okay, so this is money, so this is real stuff now, all right? So this is important. Which sequence would you prefer? Well, you might say, well, it looks like B might be the one that I prefer because more money, better stuff, right? So we might say B would be the one that we prefer. If we're only going for 1 year, then A is the best one. After 1 year, A's 27. So that's pretty good. And after 2 years, A is still better than the other ones. After 3 years, oh, there's a tie. So it really depends on how long that you want to go for. So that one depends on how many years. But based on what we have so far, it looks like B, because B after 6 years has the most. So B after 6 years has the most money. And that's all we know for right now. So let's just go with B. Say, okay, B. B looks like a good choice. All right, if you kept your money in an account for several more years, would that change your answer? Probably. Let's go ahead and use the next resource page to get to the 7th term. So we already got the 6th term right here. We're going to go to the 7th term. All right, so here's 5.3.1b, this worksheet. We've already got sequence B done for us, which was kind of nice. And now we can just finish off the other ones. Well, we already knew 5 and 6 because we did those. That's 135 and 162. So this one is 135 and 162. And we're adding by 27 each time. So if I take 162 plus 27, the next term would be 189. All right, so that's for sequence A. Now they are just connecting these so we can see the growth pattern. Remember, all of these sequences should be discrete because you can't have a term number that's not an integer greater than 1. So the 5th term will be at 135. So 5th term, 120, 135 would be right here. The next term, the 6th term would be 162. So 60. What are these going by? 5? No, they're going by 10s. So 162 we're going to say is like right here. Did I do this right? 135. Oh, dang it. This is 130. This is 135. Look at your scale. All right, so sorry about that. 7th one, 189. So this is 190. So there we go. All right, so it looks like I'm continuing on this linear path, pretty much. I did something wrong. We'll fix it later. So we're going to continue on this linear path. Oh, this is 130. This was supposed to be 135. Dang it. I really screwed that up. That's all right. All right, so Holcomb is bad at graphing. Okay, this we know. All right, so next one, B. This would be, what color was I doing B in? Light blue. All right, so we would do, we already got 4, so 5 would be 225. So where's 225 at? Here's 220, so 5, 220, looks like right here. Yeah, because this is 230, so this would be 225 right there. Okay, so we can see, it's still kind of growing there. 6 would be at 324. Wow, that's off the graph. Why didn't they give me more graph? More graph. So 6 is at 324. That's probably going to be somewhere like right up here. And then 7 is at 441, which is way off the graph. We're just going to put it way up here somewhere. So I'm still getting this nice curve, and it's still increasing there. All right, so we're just going to go boop, 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 boop. All right, there we go. Let's do sequence C now. This is our multiplying by 2, so the next one would be 96, then 192, and then a bigger number, 192 times 2. It's too early to think, not plus 2. 192 times 2, 384. I should have known that. All right, so 596. Let's see, 90 is right here, so 96 is right about there-ish. Okay, the next one would be at 6, 192. So 192, here's 190. 6 and 192 would be about right there. And then 7 and 384. Wow. Wow. 7 and 384. That's really high. That's really far off my graph. So look at what's happening for this one. And then it's going to keep on growing. You see what's happening here? Look at the distances. It's getting closer. It's getting closer. Ooh. And as it keeps on going, it's going to get closer and closer. It didn't quite make it. So this is 441, this is 384, but these two are going to be pretty close. So you see what's happening to the numbers? Sequence C started below everybody else, but now it's catching up now. All right, so that exponential sequence, sequence C, is really making up some ground since we're multiplying by 2 each time. So at the beginning, it doesn't look like it's growing as much, but over time, these sequences that multiply really start making up some room there with that curve. That curve gets steeper and steeper, so that growth is increasing. The farther along you go, it increases by more and more each time. All right. So you kept your money in the account for several more years. Would that change your answer? Yes. Yes, indeed it would. It looks like sequence C grows fastest over time. GRO. All right, we already did the sequence of 7. So what do you notice about the patterns of growth? Well, the A is linear. We notice that B was a curve. And we notice that C was a curve that grew faster as time went on. So the linear one had constant growth, the same growth every time. The growth was 27 each time. This curve grew by a non-constant rate, but we saw that it was only growing by 18 more each time. So it was, the difference of the difference was constant, but the actual rate each time wasn't the same, 27, 45, 63, but the differences were constant. Whereas in geometric, we're multiplying. So the rates get bigger and bigger as our numbers get bigger and bigger. All right, so let's think about this. If two bank accounts always start off with the same amount of money, will the exponential bank account always eventually have more money than a linear account, no matter how steep the rate of growth is for the linear account? So this is saying if we've got two of them to compare, let's say that we've got a super steep line. They're saying if I've got a really steep line, will the exponential bank account always eventually overtake that line? Well, what if there's like a really small curve? Like it was really starting off really slow. Would it catch up eventually? Yes, because we have infinity to play with. Eventually, way down here down the line, this curve is going to increase its growth. This line will never increase its growth. So no matter how flat your curve is, eventually it will be more than the linear. It might not happen soon, but since we have infinity to play with, the exponential will always overtake the linear no matter how steep the slope is of the line. So exponential will always eventually grow more than linear. It might not happen soon, but again, we've got infinity to play with here. So eventually, this curve somewhere down the line will get steep enough so that it will overtake this one right here. Eventually. Not going to happen soon sometimes, but eventually it will. And we saw on our graph that we did earlier that in this case, it was somewhere around here between the 5th and the 6th year that the exponential went past the linear because its rate of change is constantly changing. This rate of change would always be the same. If you look at slope triangles, this slope triangle is always the same. No matter what, we're getting the same exact slope triangle. That's what I messed up, Ron. I didn't go to the right part. It's supposed to be here. Wow. All right, so these slope triangles always end up being the same. Whereas if you look at the slope triangle for the exponential, really small slope triangle there, a little bit bigger slope triangle there, a lot bigger slope triangle there, and then we get bigger and bigger slopes the farther along that we go. See what's happening to, look at that. Barely anything. And then all of a sudden it just takes off and it gets super steep. So we can see just looking at those slope triangles that these exponential functions really increase their rates of change the farther down we get. Look how steep it's starting to get over here. Whereas the linear function is always doing it by the same amount. Wow, I can't believe I missed that. I was 1 over. Anyways, good times. There you go. That's all I got for you. Mistakes and all. Hope you enjoyed it. Math hard. See you guys later.